Let's take a look at a few examples out of 1.3. 1.3 deals with direction fields and isoclines and approximating solutions using direction fields. So over here we have a picture of the direction field that's generated by this differential equation. And essentially what happens is if you pick a particular point, for example, 0, 2, if you put a 0 for x, a 2 for y, it'll tell you what the slope is going to be at that point. So 4 times 0 is 0, 9 times 2 is 18, 0 over 18, the slope at that point is 0. If you pick a point, for example, this one, 2, 3, if you put a 2 in for x and a 3 in for y, the slope at that point is 8 over 27. So there's a little dash with that corresponding slope. That slope is about 8/27. Here, that slope was 0. So these dashes represent the slope at each of those ordered pairs. And that comes, again, from substituting those ordered pairs into this differential equation, and this tells us what the slope is. So A asks us to verify that these two are solution curves to that differential equation, provided that x is not 0. So I'm going to check y equals 2/3 x to see if it's a solution curve, and then I'll leave y equals negative 2/3 x for you. So if we want to check to see if there's a solution to that equation, this is an explicit solution. So we need the derivative of this. The derivative of y with respect to x is 2/3. So we can go to our differential equation, dy dx, put 2/3. In place of y, put 2/3 x. And we want to see if this is a true statement. Yes, substituting the derivative of our quote-unquote solution for dy over dx and putting our solution in for y gives us a true statement, then yes, indeed, that is the solution. So here, 3 goes into 9 3 times. We have a 4 on top, a 2 on bottom. 2 goes into 4 twice. And the x is reduces to 2 on top, 3 on bottom, which is exactly what the left side is. So by substituting the derivative and substituting the value of y in to our differential equation, we demonstrated that y equals 2/3 x is indeed a solution to that differential equation. So now they want us to sketch a particular solution under the initial condition that when x is 0, y is 2. So when x is 0, y is 2, so sketch that solution. So remember that the slope here was 0. So we start out, we're kind of horizontal. As we get farther to the right, our slope is positive slightly. So we're slightly going up. The farther we go to the right, we're getting steeper and steeper and steeper. And it even looks like we're following that line. If we go to the left, the farther we go to the left, we just want our curve to match the slope given by the direction field. So our solution would look like that. Remember, when we integrate, we get a family of solutions. So essentially, this is one particular solution under the initial value 0, 2. So then part C says, all right, what if x is 4 and y is negative 1? So 4 and negative 1 would be here. So sketch that curve. So as we go farther to the right, we're going to do this. If we go to the left, we're getting steeper and steeper and steeper until we're vertical. And then as we go up, our slope becomes positive. So that's going to actually take us back this way. So there's the solution curve for part C. Now, part D, I'm going to answer this for, it says what can be said about the behavior of the above solutions. So it means the solutions for B and C. So I'm going to do for B. So what can be said about the behavior of the solutions for B as x goes to positive infinity and as x goes to negative infinity? So if we look at the curve of our solution for B, as x goes to positive infinity, so as we're going to the right, then our curve is getting closer and closer to that line. So as we're going to positive infinity, we approach that line, and that line comes from these two straight solution curves that were drawn. This line is the positive one, so it approaches y equals 2/3 x. As x goes to negative infinity, so as we go to the left, then we're approaching that curve. We're following, that was the one, y equals negative 2/3 x. When we're going to positive infinity and we're following y equals 2/3 x, notice that's going to be going up and up and up forever. So we're going to positive infinity in the y direction. Here, as we're going towards negative infinity in the x direction, so as we're going farther and farther to the left, we're following that line, and it's going up and up and up and up forever, so it's going to positive infinity in the y direction. So they just want to know which curve are we following. As we go to the right, we're following y equals 2/3 x. As we go to the left, we're following y equals negative 2/3 x. When we go to the right, we're going up forever. When we go to the left, we're going up forever. Now, we're not always given the direction field, so sometimes you have to sketch it. So that's what they want us to do on this one, to sketch the direction field. And it says to use the method of isoclines. And what that does is, so dy over dt. So C represents the slope. It's the slope of our curve at any given point. So notice this one doesn't have y's and t's both in it. Our slope is determined simply by the y value. So I want to know when our slope is 0. So when c is 0, when is that? So if we set this equal to 0, we can factor out the y. And we get, when we have a slope of 0, that occurs when y equals 0 and when y equals 4. Those are the two times where we have that particular slope. Now we could do when c equals other values, or we could use different y values to get different slopes. So several different ways we could go about doing this. So let's see about pulling up some graphs here. So when y is 0 and when y is 4, we have a slope of 0. So if we come into our graph, when y is 0, we have a slope of 0. So y is 0 here, our slope is 0. Y is 0, slope of 0, slope of 0. So when y is 0, we have no slope. So I'm going to put a dash that has no slope. Also, when y is 4, we have no slope. Our slope is 0. So up here, we have no slope. Now, there are different ways to go about this. Generally, with isoclines, we're going to let C be a constant. We're going to put a constant value in for C, and we're going to find, okay, for those constant values, where do we have that particular slope? Since this only has one variable on the right, only y, then that means at particular y values, all of those slopes are going to match. So let's do it this way. So let's write that our slope for y minus y squared. So let's pick a y value and determine what the slope is going to be at that y value. So we've got 0 and 4. We know that the slope is 0 there. If we let y be 1, when the y is 1, we have a slope of 4 times 1 minus y squared, or 1 squared. So we have a slope of 3. So anytime y is 1, when y equals 1, our slope is 3. So that would look something like this. And we just draw all of those roughly 3. And then we can go in and say, okay, what about when y is 2? When y is 2, we have 4 times 2 is 8, minus 2 squared. So this time we have a slope of 4, so that's getting a little bit steeper. So when y is 2, a little bit steeper. And then what about when y is 3? So if we put a 3 in, 4 times 3 is 12. 3 squared is 9. So then we're back to 3. So now we're back to having a slope of 3. All right, so let's do some that are, let's do a couple above the blue dashed line, and then a couple below there. So let's do 5. So, no, don't do that. When y is 5, we have 4 times 5 minus 5 squared. So that's a slope of negative 5. So that's pretty steep. And it's negative, so it's going down. Lots of little dashes. Bob Ross would say lots of pretty little dashes. Y equals 6. 4 times 6 is 24. 6 squared is 36. So that's the slope of what? Negative 12. So that's really steep. Almost straight up. Not quite straight up, but it's very, very steep. And then let's pick some below the bottom dash. So let's pick negative 1 and negative 2. So if we put a negative 1 in, 4 times negative 1 is negative 4. Negative 1 squared is 1, so we get negative 5 here. So that's pretty steep. If we pick negative 2, 4 times negative 2 is negative 8, minus negative 2 squared, so negative 2 times negative 2 is negative 4, so negative 12, so again, almost straight up. So this is a direction field, and these are actually isoclines because on this line, all of these have the same slope. On this line, all of those have the same slope. Here, all of those have the same slope. So here's a direction field. Now, if this were going to be, let's say, population, our population is going to be positive, our time is going to be positive, so we might restrict that to only being the first quadrant. So we might want to look at a couple of particular solutions. We might want to look at what if our population, initial population, was 1? What would happen? So we would start out, our population would go this way, and then we have a quick growth. It's getting pretty steep, but then it starts to flatten out until it levels off. If we had a population that started here, then it's going to quickly decline, but then the decline is going to be less, and the decline is going to be less, and then we're going to level off there. So either way, our population is leveling off towards the same value of 4. If we start low, then we're going to have a quick growth, but then it's going to start leveling off. If our population starts too high, we're going to have a sharp decline, and then our population is going to level off. All right, so let's look at another example. Here's another one where they want us to draw the direction fields. I'm mashing the wrong button there. The direction fields using isoclines, and then include some solutions. C equals x plus 1, and again, C is just the constant that's going to represent various slopes. Now notice here we have 2 different variables, and if we solve this for y, C, which is a straight line? That's a straight line. So C is just the different y-intercepts. So if we let C be different values like 0, 1, 2, 3, those are going to correspond to different y-intercepts. And we're going to have a slope of -1 on each of those. So how's that going to work? So let's look at the graph of that. We write out that relation y C, then when C is 0, we would get the equation y equals, which has a y-intercept of 0 and a slope of -1. So I'm going to draw a line here, and we're going to come back and take that line off later. But everywhere on this line, the C value is 0. And remember what C stands for. C is the slope. So everywhere on this line, we have a slope of 0. So I'm going to put little dashes that have no slope. So that's the isocline that corresponds to C being 0. And then if we wanted to, we could take that line off. So now let's look at, I'm going to do these different colors. Let's look at C being 1. So if C is 1, we have a y-intercept of 1, a slope of -1, so that would be this line. So everywhere on that line, C is 1, and again, C represents the slope. Remember, we replaced our slope with C. So everywhere on that line, we have a slope of 1. So I'm going to put little dashes that have slopes of 1. So don't be confused with the slope of the direction field and the slope of the isocline. When we use this equation, it has a slope of -1. That just generates the line on which all the slopes are the same. Now, sometimes our isoclines are not lines. Sometimes our isoclines are different shapes. But what makes it iso is that everywhere on there, something is the same, and what's the same is that C, the slope, is the same everywhere on that line. So on that line, the slope is -1. If we change C to, let's do C equals 2, if we put a 2 in for C, then our isocline would be here. And on that isocline, C is 2, meaning we have a slope of 2 on that line. So we have a steeper slope on this line. The actual line that we drew has a slope of -1, but the dy over dx on that line is 2. When C is 3, so if we change C to 3, our isocline has a y-intercept of 3, but the slopes that occur on that isocline are slopes of 3. So I'm going to approximate slopes of 3, and I'm going to go down this isocline and put the same slopes throughout. Now let's do some negatives. Let's do C equals -1. So if C is -1, then our isocline is down here. And everywhere that we're on that isocline, our slope is -1. So a negative slope is going down the slope of -1. If we change to C equals -2, then our isocline is down to -2, and everywhere, I keep doing that, everywhere along there, everywhere on that line, then our slope is going to be -2. So a slope of -2 is like this. The good news is that while this is a lengthy process, there are computer programs and lots of different things that generate these direction fields for you. Now that we've drawn these, then let's sketch a solution or two. So let's suppose we start out with an initial value of 2. So if we start out with an initial value of 2, if we go farther to the right as we go, we're going up, and it looks like we're getting steeper and steeper. As we go to the left, we're coming down. We're going to be flattening out. Here our slope is 0. As we go farther to the left, we start getting a negative slope. And we're going to be kind of following in this direction. Let's say we start out with a value of -1. If we're at -1 and we take a slope, notice we stay on that line. We're staying on that line. If we start out with a value like -2, as we go up, we're going to be turning, and we're going to be following that line. As we go down, we're going to be getting steeper and steeper in the negative direction. So here, let me take this isocline here off. So we're just following those direction field lines to make our curves. So there's one more where they ask us to do this. So let's see if we can go through this kind of quickly. So we're going to replace our slope with C. And let's solve this for y. So multiply by x, divide by 2. So y is C times x over 2. Or we could spread that out a little bit and call that C over 2 times x. Which, if C is a constant, Then this is a straight line. Our isocline is a straight line again. All of these isoclines, notice, have a y-intercept of 0. And then the slope of the isocline is half of c. Remember again, c is dy over dx, which is the slope of the direction field, or the slope of our solution curve, you could say. So slope of the solution curve. That divided by 2 is the slope of our isocline. Let's sketch a couple. Try to do just enough to give you the general idea here. So let's write our equation for our isocline. Y is b over 2 times x. So let's do c equals 4. Let's do -2 and c equals 4. So let's do those 5. So if c is 0, we get y equals 0. So y equals 0 is a horizontal line known as the x-axis. So everywhere we're on that horizontal line, that's our isocline. We have a slope of 0 on that isocline. So I'm going to go into that isocline, and I'm going to put dashes with a slope of 0. Remember, c is just in place of dy dx. Alright, so I'm going to erase that isocline. So now let's go to 2. We have 2 over 2 times x. So the equation of the isocline is y equals x, which is just a straight line here. Straight line with a slope of 1, a y-intercept of 0. The slope of our direction field on that isocline, remember, is c. So the slope, not the slope of this line, but the slope of the direction field on that isocline is 2. So everywhere we're on that line, we're going to go in and put a dash with a slope of 2. Now 4. So let's delete this. And now let's let c be 4. So when c is 4, the equation of our isocline is 2x. So if we graph that line, that isocline is here. So on that isocline, our slopes are 4. So approximate a slope of 4. Pretty steep. Uh-oh, I missed it with that one. All right, and then let's delete the isocline. Now when c is -2, the equation of the isocline is -2 over 2, so -1x. So that gives us this line. Everywhere on that line, we're going to have a slope of -2. D is dy dx, so a slope of -2. So a slope of -2 would be something like this. So these little dashes just indicate which direction our curve is headed. Which direction our curve is headed, the steepness of the curve at each of those values. When C is -4, we get Y X. So let's again draw that isocline. So if we have a slope of -4, it'll be about here. And on that line, I said it wrong, didn't I? See, it's easy to run those two together. The slope of our isocline is -2. Let's put in some black dots just for. So we have a y-intercept of 0, a slope of -2 for the isocline. And we could draw the line through that. But remember what we're really after. We're after that we're going to plot slopes of -4 everywhere that we're on that line. So on that line, our slopes are -4. So our slopes are going to look like this. So while that has lots of gaps in it, that gives us a rough idea of what our direction field would look like. We could pick C to be some fractional values so that we have some slopes that are just a little bit above 0. We could get some negative small values so that we have slopes that are just barely negative, so that we could get a little bit clearer picture. But that's a rough picture of our direction field.